Hello, my name is Brendan Fries, and today I'll be talking about optimizing quantum computing on a classical computer. Classical computing relies on bits and Boolean algebra, which can solve a larger variety of problems, but for some specific problems, it can be quite slow, which is where quantum computing comes into play, which relies on qubits to use superposition and entanglement in various materials. For the mathematics, it requires linear algebra on complex values. Because of this, the algorithms implemented with quantum computing are not very general purpose, but they can be extremely efficient for some problems. Simulating quantum computing is an important process of the pipeline to process calculations on a quantum computer. Access to quantum hardware is still very limited. With that, they are generally very expensive to run and build. With that, testing and verifying algorithms on classical hardware before running them on quantum is a really nice process to make sure that your algorithms are working without having to go through an expensive process of running a quantum computer. Some background knowledge is on exponential runtimes. In computer science, we evaluate algorithms by how their runtimes change in response to the size of the input. Exponential algorithms are intractable with sufficiently large input, no matter how good the hardware is. Some algorithms are linear on quantum computers, but exponential on classical ones. To run our optimization test, we're going to be using a Python package called QCPy, which me and a few other developers implemented to help beginners in quantum computing who are CS backgrounds or either students or professionals in the field to understand its capabilities and to simulate basic quantum computing algorithms. It is very malleable to suit specific needs of the user. So a baseline QCPy implementation is a very naive approach. It takes the mathematics that are used on a quantum computer as is and then implement it on a classical computer with no optimization processes. This causes an extreme runtime deficiency where about 11 qubits given any significant quantum circuit will not be able to run in an efficient manner. Sorry. The first optimization process that we can do is called sparsing, which is well known in high performance computing. It's where you remove any idea of there being zeros in your matrices when you're doing calculations, instead only holding information of any value greater than zero. This is very nice for quantum computing because quantum computing matrices have a very large amount of zeros within its space. So this increases space efficiency if matrices are actually sparse, but there's extra runtime overhead to convert matrices to this representation. And when coming back to the previous slide of pure quantum computing mathematics, this actually causes extra runtime complexity on top of your computing. Another optimization process you can do is improving the CNOT gate, which is an essential part of quantum computing if you want to work with multiple qubits at once. It uses classical XOR logic to entangle 2 or more qubits. In a vector space, the CNOT gate itself cannot span across more than 2 neighbor qubits. Usage of quantum gates to construct logic of multiple control qubits and spanning across quantum circuits. On classical computers, this can cause extreme efficiency issues. The solution for that is using Bra-Ket notation on each control qubit and use that to create a singular matrix to apply onto the quantum circuit. A third optimization technique you can do is using compiled matrices. Many quantum algorithms rely on applying the same 1 qubit quantum gate to multiple qubits, such as putting a Hadamard gate on every qubit before you actually go through the process of your algorithm. Instead of implementing each transformation individually, you pre-compile all of these gates into a single matrices and then apply that matrix to a multi-qubit system. There's no downside when you are allowed to use this or when it is a part of your algorithm or quantum circuit. A fourth optimization technique is using a GPU or a graphics processing unit, which are widely used to accelerate linear algebra computations, including quantum computing simulation. We are using our NVIDIA GPU, and we're specifically using the QPy library, which allows us to implement Python code into our NVIDIA GPU. It can improve runtimes, but not change exponential nature of quantum simulation. For our environment setup for running our tests, we have three specific core points of our hardware. Our CPU is a Intel i7 with 4 gigahertz. Our RAM is 16 gigabytes of DDR3, and our GPU is an NVIDIA GeForce GTX 1070 with 1920 CUDA cores. So this is a pretty medium grade computer that is several years old, which is a great idea to run our code on, as it's not an extremely efficient computer, nor is it an extremely poor computer. For our optimization tests, we're going to be running tests implementing the Grover search algorithm using sparse matrices, but still relying on the core quantum computing mathematics, sparse matrices, and CNOP-Bra-Ket algorithm together, and then finally combining those two with the compiled matrices. With that, we're going to take a look at the GPU using pure quantum computing, and then combining all optimizations and running the simulation on a GPU. As you can see, based off of our results, you can notice that sparsing does indeed cause an extreme overhead. With our runtime in seconds, it gets to about 51 seconds in order to compute 11 qubits for our Grover search algorithm. It starts to decrease significantly, and on the brown line is our final computation, where we apply everything on the GPU using the CNOT algorithm, sparsing, and compiled matrices. To get our speedups at 11 qubits, you can see that the final result is around 470 times faster than the base, while as sparsing, for example, is significantly lower at this level of qubits. Conclusion: many optimizations can be implemented to better enhance quantum computing on a classical computer. These optimization techniques are still limited by the core process of determining the output of a circuit.